Greetings everyone, I am Bharat and I will be presenting our paper metaKanren towards a relational metacircular interpreter. Firstly, I would like to motivate our problem. So on one hand, we have relational programming, which is all about expressing computer programs as mathematical relations. On top of this, we have relational interpreters, which are interpreters for programming languages written in the relational programming paradigm. These have been used to solve several interesting problems. For example, there's Barleman, the relational scheme interpreter, which has been used to do things such as coin generation and turning proof checkers into theorem provers. On the other hand, we have metacircular interpreters, which are interpreters where the interpreted language is same as the interpreting language, reducing the meaning of all possible programs to the meaning of one particular program, the metacircular interpreter. Thus, we unify these two fascinating ideas and ask if we can have a metacircular relational interpreter. One natural way to go about implementing metacircular interpreters is to simply syntactically translate every expression in the interpreted language to a corresponding expression in the interpreting language. Such a translation is called a shallow embedding. So, let's take a look at a shallow relational interpreter for a tiny relational language to understand its shortcomings. The language we look at is quite minimal. All it has is unification, fresh so that we can introduce new logic variables, conjunction and disjunction. The only arguments allowed in a unification are logic variables or quoted datum. Although this language is quite minimal, for example, it does not have numbers or cons pairs, it is still useful to understand the limits of expressivity of a shallow interpreter. Let's see how we would go about writing a shallow interpreter for this tiny relational language. Our interpreter is the two-argument relation eval programo between the program and the output of the program. The program is a run1 expression with a query logic variable, which is a symbol, and a goal expression. To evaluate the program, we evaluate the goal expression of the program by creating an environment where we map the query logic variable to the output logic variable. This is how we will be using environments throughout the interpreter. That is, we will use the environment to map source logic variables to host logic variables. Let's see how we evaluate goal expressions. To evaluate a goal expression, we first look at the kind of goal expression it is. If it is a unification, we translate it into a host unification by having both the term expressions E1 and E2 here evaluate the same term t. To evaluate a fresh expression, we extend the environment by mapping the source fresh logic variable to a host fresh logic variable. Here x is being mapped to x1 and then recursively evaluating the goal expression in the fresh. A conjunction is translated into a host conjunction and disjunction is translated into a host disjunction, which is condi here. Term evaluation is also quite simple. We have symbols which are self-evaluating, and then we have logic variables which are simply looked up in the environment. Lookup is pretty much what you would expect because we use association lists for environments. We first check if the car of the first element is what we are looking for. If it is, we unify the value with the CUDA. Otherwise, we recursively search through the rest of the association list. Now that we have walked through the shallow interpreter, let's see it in action by looking at a few examples. First, let's look at a fairly straightforward unification. The inner run query unifies the inner query logic variable with the symbol cat, and the outer query variable is the output argument to the shallow interpreter. As expected, we get back cat as the only possible answer for this query. Now let's try to perform program synthesis by providing the expected output as cat and replacing a part of the program with the logic variable x. Here, in addition to what one might expect, which is the symbol cat, we also get back another answer, which is the symbol z, the inner query logic variable. To understand why this is the case, it is useful to replace x with z and run the query forwards. Here, miniKanren tells us that the outer query logic variable x is fresh. What this means is that when we have a unification of an inner query logic variable with itself, the output is allowed to be anything, because anything always unifies with itself. This is because the way we have implemented the shallow interpreter, z gets unified with the output, which is cat in this case, and then equal z is translated to equal cat, which succeeds. Now, with that in mind, let's look at a slightly more complicated synthesis query. Here, let us try to synthesize the branches of a disjunction by providing the expected output as cat. The first two answers are explained by the previous behavior. We have an inner query logic variable. We have an inner logic variable being unified with itself, letting the output be anything. The next two answers are more interesting. They tell us that if one of the branches unifies the inner query logic variable z with cat, the other branch can be anything. This demonstrates an important limitation on the expressivity. With the shallow interpreter, we cannot express negative examples. What I mean by that is we can say what one of the answers should be. For example, here we say that one of the answers should be cat, but we cannot say what all possible answers are. To say what all possible answers are, we need to have run star queries, because that's how run star is defined. It finds all possible answers for the given constraints. But we cannot implement run star in a shallow interpreter, because to collect all answers, we would want the interpreter to express which goals succeed and which goals fail. If we try to do this with a syntactic translation, we would have to express which goals succeed and which goals fail in the host language, which is miniKanren. This goes against the relational nature of the interpreter. But if we don't rely on a simple syntactic translation and instead have an explicit representation for the goals in the source language, then we can express which goals succeed and which goals fail as conditions on this representation. Such an implementation where we have explicit representation for the source language is called a deep embedding. The key takeaway here is that we cannot implement run star semantics with a shallow embedding. And this is where metaKanren comes into the picture. It is a microKanren-like language for which we have implemented a deep relational interpreter. Now, I'd like to show some example programs in metaKanren, but before that, there are a few syntactical differences between metaKanren and microKanren that I'd like to go over. The way I'll be going over the syntactic differences is I'll take a valid microKanren program and massage it into a metaKanren program by making one change at a time. The program that I'll be using is 5s and 6s, which is a simple one argument relation which unifies its argument with 5 or 6 and then recursively calls itself. So what we end up with is an alternating stream of 5s and 6s. The first change we make is based on the fact that miniKanren does not have Arabic numeral arithmetic. And this is important because we use Arabic numerals in the counter that we provide to run. For instance, here we provide 3. Because miniKanren does not have Arabic numerals, we use an alternative representation, what we call piano numerals. Here we represent 0 by the empty list and the successor of n as n wrapped in a singleton list. For example, because 0 is the empty list, 1 would be 0 wrapped in the empty list, wrapped in a singleton list, 2 would be 1 wrapped in a singleton list, and so on. Thus, the first change we make is we replace 3 on the first line with the piano numeral 3. Now, the second change is based on the fact that letrec is used to create the user-defined relation 5s and 6s, and procedure application is used to call 5s and 6s. Because microKanren is embedded in scheme, this works fine. However, we want metaKanren to run in miniKanren, which does not have letrec or procedure application. So what we do is we extend the source language with letrec rel to create recursive relations and call rel to call a user-defined relation. Finally, we are still using lambdas here to delay computation. Once again, because miniKanren does not have lambdas, we introduce another construct into the source language, delay, which is used to delay goal evaluation. In summary, the 3 changes we made were piano numerals for the run counter, letrec rel, and call rel, and delay. Now let's look at some metaKanren examples. The first example that we'll be looking at is the usual 3-argument appendo defined in metaKanren. It concatenates the lists L1 and L2 into the list L. Here we call it by providing it the lists 1, 2 and 3, 4, and we run it forwards. Thus, the expected output here is the list 1, 2, 3, 4. Let's run it to make sure that is indeed what we get. As expected, we get 1, 2, 3, 4. It must be noted that it is wrapped in an extra list because metaKanren itself runs in miniKanren. Now let's run it backwards by providing what the expected output is and replacing a part of the program with a logic variable. Here we have replaced this conjunction with the logic variable x, and we have provided the expected output. Let's run it to see what we get. Also, it must be noted that we use run star for the inner query, which was not possible with a shallow interpreter. As expected, metaKanren correctly synthesizes the fragment to be a conjunction, to be conj. Now, let us go back to the motivating example where we had claimed that having a run star is more useful than run one when it comes to program synthesis. Here, instead of run star, let's see what happens if we provide a run one and try to again synthesize x. This time, in addition to conj, we also get back disj. Notice that when we had run it with a run star, we had only gotten back conj. This is precisely the expressivity that a run star in the source language brings to the table. Now, there's a technique I'd like to present which we have found to be useful when it comes to program synthesis. I think this technique is novel in the sense that it would not be applicable if we were doing program synthesis with the relational scheme interpreter because of the difference in the nature of the source languages. That is, scheme is functional whereas metaKanren is relational. Let's look at the technique. Here we have a simple one argument user defined relation 5O which unifies its argument with the Arabic numeral 5. We can call this relation using callrel and then get 5. Now let's see what happens if we try to perform program synthesis by providing it the expected output and inserting logic variables into the program. Here we have put in E1 and E2 instead of 5 and F, and provided the expected output as 5. It must be noted that reification of answers also uses piano numerals, so instead of _0 you have underscore the piano numeral 0. Let's see what metaKanren synthesizes for E1 and E2. Here it synthesizes metaKanren tells us that E1 and E2 can be anything as long as numbers. This may seem confusing, however, this answer is in fact correct because what's happening here is the logic variable z remains fresh. In other words, it is sufficient for 5O to succeed without having to do anything with its argument f. In fact, if we asked for more answers, we would eventually get back what we expect, which is 5 and f. If we asked for 4 answers instead of 1 answer, we would get back 5 and f at some point. Here, the first 2 answers are spurious, then we have 5 and f. The way to get around this is by grounding the logic variable externally. That is, instead of 5, we put in z here, and then instead of having z fresh, we say we have 5 here. We call this external grounding. When we run this, we don't get spurious answers anymore. Instead, we get 5 and f. Finally, I'd like to touch upon the limitations of the current interpreter. Firstly, it's quite slow because we don't do any optimizations. The goal with the work so far has been to have more expressivity. Some techniques we'd like to explore to improve the performance are partial evaluation to overcome the interpretive overhead, use techniques from Barleman, and also guiding the search. On the other hand, we would also want metaKanren to be metacircular. Currently, metaKanren does not implement disequality, absento, and data type constraints. Furthermore, metaKanren does not support mutually recursive user-defined relations. Finally, it would be useful to have a relational parser for things like condy, as currently everything must be written using disj and conj, which makes the programs quite verbose. That's it for my talk. Hope everyone enjoyed it. Questions and feedback are welcome. If you would like to access any of the code, it's available on my GitHub repository. You can also Google search for metaKanren and I believe the repository comes up.